Okay, we're going to, real quick, I'm going to do example 12, and then I'm going to have to take a little hiatus, and I will get this out to you by 3:30 or so, I'm hoping. It's 1 o'clock today. I got to go teach a class here in a minute. Um, here we go. Here's the problem. We're going to look at this problem here. We're going to do example 12. All right, so an equilibrium problem means that we're holding everything up. Everything we're holding up is all the forces are equal to zero. Okay, so he's got this tension in this rope here and this tension here and the weight of this engine, and he's just sitting there holding it. Okay, and we want to solve for the tension in one and the tension in rope two. All right, it won't be that hard. Trust me, I'm a doctor. No, anyway, all right, so here we go. Okay, so this is 80 degrees off that. Yeah, I don't like what they're doing. I don't see how they're measuring things off the y-axis. I don't, homie, don't play that. I like measuring things off the x-axis the way you learned it in the original thing. So I'm going to do it a little bit different, but you can take a look at it. You can see. But now, the main thing with equilibrium, sum of the forces in the x direction equals zero. Sum of the forces in the y direction are equal to zero. All right. An automobile engine has a weight. Okay, so let's find out what we know. The weight of the engine is 315 newtons. All right. I'm going to redraw it. Here's my coordinate axis system. They've got T2 coming this way. They've got the weight of the engine coming this way. All right, at 310 newtons, which is not, I mean, so we don't have to do the mg for that. And we've got a tension. Now notice there's no normal force here, but we've got this tension coming up here this way. This is 10 degrees off this axis, and this is 80 degrees off this axis. So I'm flip-flopping. This is T1 up this way. There's our free body diagram. All we have to do, and this is T2. Okay, so I've got two unknowns. I've got two unknowns. But how many equations am I going to come up with? Two. Therefore, I can do this. We got this. There's nothing to this. All right? So let's take the sum of the forces in the x direction equals zero for our first equilibrium. And I'm going to break T1 into its two components, T1x. I'm going to break T2 into its components, T2x. It's going this way. And there's T1y, and there's T1y. Or T2y and T1y. I can't look at it I can't measure things off the y-axis. I'm slow. I can't do that. So I set it up this way. Why did I write Ty so crooked? It's coming straight up like that. All right. So the sum of the forces in the x direction is equal to 0, which is equal to minus T1x plus T2x. Hey, we're on to something. So T1x equals T2x. That's interesting. All right. What does T1x equal? T1x is equal to T1 times the cosine of 80. T2x is equal to, now these are the magnitudes of them. T2x is equal to T2 times the cosine of 10. All right. Okay. So I can set these up. So I can say, well, T1x is equal to T2x. And so T1x, so T1 is equal to T2 times the cosine of 10 divided by the cosine of 80. Right away, I know some of you go, where'd you get that? Where'd you get that? Well, T1x is T1 times the cosine of 80 divided by the cosine of 80, both sides, you get that. So T1 is equal to that of T2. All right, because remember, back in 8th grade algebra, when you had two unknowns, you had to find one in two equations. You solved one for one and substituted in for the other. So let's look at the sum of the forces in the y direction. This is so much fun. Sum of the forces in y direction also equals 0. And I've got T1y. I got a positive T1y here. Minus T2y. Minus 310 newtons, which is the weight. Okay? So I go, all right, well, 0 is equal to T1y, which is T1 sine of 80 plus minus T2 sine of 10 minus 310. All right. Now we do the substitution. We're going to take this stuff, plug it in down here. So I've got T2 cosine of 10 divided by the cosine of 80. That times the sine of 80 minus T2 sine of 10 minus 310. This is all equal to 0. So 310 is equal to, I'm going to factor out the T2. T2 times the cosine of 10 or the cosine of 80 times the sine of 80. Now, some of you might be going, well, why don't you just make the sine of 80 sine over cosine is tangent? You can do that, but we don't need to, minus the sine of 10. Let's figure out what this mess is. Divide it by 310. So when I find out what the mess is there, when I take the cosine of 10 divided by the cosine of 80 divided, oh, okay, I want to make sure I do this right on my calculator. So I am going to change this to T2 just to keep it straight. Cosine of 10 times the tangent, so everything's going straight across, times the tangent of 80 minus the sine of 10. Okay? So I got cosine 10 times the tangent of 10, tangent of 80, gotta be careful, minus the sine of 10. Yeah, there's a little bit of mathematics involved here. What the heck? That cannot be right. Oh, wait a minute. That tangent of 80 could be huge. Oh, yes, the tangent of 80 is huge. The tangent of 80 is huge. Look, I was going, wait a minute. I thought all these, the tangent of 80, that's a big number. It's 5.67. Yeah. All right, so I wind up with 5.41. 5.41 T2 is equal to 310. So T2 is equal to 310 divided by 5.41. I didn't even look at the book's answers. I don't care. So the tension for T2 isn't much. Notice the tension there isn't much. Tension for T2 is 57 newtons. And so he's using 57 newtons to hold up this 310 Newton engine. So T1, that's how much he's pulling. So he doesn't have to pull very much. So T1, let's go ahead and finish this. Whoops. So then T1 is equal to T2 cosine of 10 divided by the cosine of 80 from earlier scratch work. Which is 57. This number is going to be much bigger than that one. No, this one's going to be much bigger than that one. Times 50, T2 times Oh, I'm just 57.3 times. So I'm just going to go with the answer that we got before times cosine of 10 divided by cosine of 80. 324. This all makes sense to me. T1 equals 324 newtons. There we go. Done here. Kind of tricky, isn't it? You just keep your things in order. Now, what I wanted to end real quick with a little thing on tension. Here's the thing on tension. Let's say I got two people holding onto a rope. One of these days I'll learn how to do that. They're pulling on each other. They're not moving. They've created a tension here. All right. Action-reaction forces. T. They're equal and opposite to each other. He's pulling him this way, and the reaction is he's pulling this way. All right. So that's the way tensions work also. Okay. I think, so non-equal, yeah, so let's look at the, I want to look at example 15 next. All right, so we'll start there.